Hello, I'm Zélia da Rocha from the University of Porto, Portugal. It's such a pleasure for me to participate in this international congress from classical to modern analysis dedicated to the memory of our dear colleague, Professor José Carlos Tornillo. The title of my presentation is Some Semi-Classical Properties Obtained via Symbolic Computation of Perturbation of a Second-Order Self-Associated Orthogonal Sequence. But before I begin, let us celebrate the life and work of José Carlos Tornillo. José Carlos was a great mathematician, a very good person, and an excellent colleague. I met him several times at the University of Porto and Coimbra. For example, this photo at the left was taken at the University of Porto in 2004 on the occasion of the PhD defense of Angela Macedo. So we have from the left to the right, Pascal Maroni, advisor, Calfadouac, and José Carlos. This photo at the right was taken by Kenya Castillo at José Carlos' office. It was in 2018. José Carlos was working with Pascal Maroni. Also, I remember a day I went to the Coimbra in 2017 for giving a seminar. We had a nice discussion about orthogonal polynomials. It was a very nice day for me. So we all miss you, José Carlos. In that seminar, I presented these two papers, a general method for deriving some semi-classical properties of perturbed second-degree forms, the case of the Chebyshev form of the second kind, and on the second-order differential equation satisfied by perturbed Chebyshev polynomials. So when Kenya invited me to participate in this congress, I had the idea of extend these works to another second-degree form, apply the general method and the symbolic algorithm to another second-degree form and get results with my software written in the mathematical languages. The general method is based on results and formulas obtained by Pascal Maroni in these two articles, Une théorie algébrique des polynômes orthogonaux, application aux polynômes orthogonaux semi-classiques, and an introduction to second-degree forms. So the crucial point is that a perturbed of a second-degree form is semi-classical. Let's recall the definition of second-degree form and semi-classical forms. So a regular form is a second-degree form if there exist two polynomials, b and c, such that its formal Stieltjes function, given by this identity, satisfy a quadratic equation of this type, where d is a polynomial depending on b, c, and the form. The formal Stieltjes function is a formal series at infinity defined in terms of the moments of the form. A regular form is a semi-classical form if there exist polynomials a, c, and d, such that its formal Stieltjes function satisfies an affine equation where appears the derivative of s. Examples of second-degree forms, the four Chebyshev forms, are the most well-known second-degree forms, and the form of the second kind is the fundamental example. Among the classical forms of Hermite, Laguerre, Bessel, and Jacobi, only certain Jacobi forms are of second degree, where the coefficients satisfy these inequalities, and have this expression. For example, Legendre is not of second degree. All second-order self-associated forms are of second degree. every form obtained from a second degree form by a transformation that preserves the quadratic character of the Stieltjes equation, the shifting, the association, the perturbation, inversion, multiplication by a polynomial, for example. Let us recall some background. Pn is a monic orthogonal polynomial sequence, MOPS, with respect to a form given by its moments, if and only if there exists two sequences of coefficients, the so-called recurrence coefficients, such that Pn satisfy the following linear recurrence relation of order 2. The associated sequence of order 1 of Pn is defined by this equality. So the form acts on the variable t, and the result is a polynomial in the variable x. The associated sequence is orthogonal with these recurrence coefficients. The associated sequence of order R can be defined by recursion in terms of the associated sequence of order R minus 1. It is an orthogonal sequence with these recurrence coefficients. AMOPS Pn is a second-order self-associated sequence if and only if the associated sequence of order 2 of Pn is equal to Pn. Or equivalently, beta n plus 2 is equal to beta n, and gamma n plus 3 is equal to gamma n plus 1. Then, beta coefficient of even order are equal to beta 0, and beta coefficient of odd orders are equal to beta 1, and the same situation occurs with the gamma coefficients. These sequences are of second degree because the corresponding forms satisfy the following quadratic Stieltjes equation. And this result was given by Tonsi and Maroni in this article, the second-order self-associated orthogonal sequence. The authors show that these forms are semi-classical of class less than or equal to 3. They classify this form into 5 groups depending on the roots of the directal polynomial phi in the functional equation. The simplest group corresponds to the Chebyshev sequence of the second kind, and the 4th group corresponds to a semi-classical sequence of class 1 with this polynomial phi of degree 3 and psi given by this equality, and recurrence coefficients beta n equal to minus 1 power n, gamma n plus 1 equal to minus a quarter. So this sequence that I have called it SOSA 4 because it was the 4 group they found, this sequence will be the starting point of this work. We will consider some perturbation of it and make explicit some of their semi-classical properties, namely the differential equation. So we are going to consider 2 types of perturbation of this sequence. Perturbation by translation of order R, we modify the beta coefficient at order R by adding to it a parameter. Perturbation by dilation of order R, we modify the gamma coefficient at the order R by multiplying it by a parameter. So in the sequel, we will give results obtained via symbolic algorithms for the first perturbation by translation and by dilation. But we are able to obtain results for any fixed order R of perturbation. The Stieltjes function of a perturbed form of order R in terms of the Stieltjes function of the original form is given by the following closed formula where appears this polynomial, the so-called transfer polynomials. The transfer polynomials are given by these equalities in terms of the parameter of perturbation, the gamma coefficients, and all these polynomials. So if the order of perturbation is I, This involves a lot of algebraic manipulation. So here we have the Stieltjes function of some perturbation of Sosa form. So we'll determine the transfer polynomials in each case, and we compute the closed formula of the Stieltjes function of the perturbed form. So the parameters of a perturbation appears has a factor in these formulas. Given a second-order form satisfying a quadratic Stieltjes equation, its perturbed of order R still is a second-degree form, because it satisfies the following quadratic Stieltjes equation with the coefficients given in terms of the coefficients of the original equation and the transfer polynomials defined so far. Here we give the results for the two types of perturbation. So we start from the coefficient B, C, and D of Sosa 4. The perturbed coefficients are given here. It is important to try to factorize these polynomials in order to cancel any common factor. Also, the polynomial B tilde is always taken monic. The perturbed of second-degree form is a semi-classical form, because from the quadratic Stieltjes equation, we can obtain the functional equation and a fine Stieltjes equation of the perturbed form. All this in terms of the coefficients of the quadratic Stieltjes equation. The class of a semi-classical form can be determined from the fine Stieltjes equation by this equality in terms of the degrees of the polynomial C and D, if A, C, and D have no common factor. The class can also be determined from the functional equation by this equality, also in terms of the degrees of polynomials phi and psi, if this condition is verified, where C is any root of the director polynomial phi. If this condition is not verified, the functional equation can be reduced in this way, and the class decreases by one unity. So it's more easy to determine the class of the semi-classical form from the affine Stieltjes equation. Here are the results in each case. It is important to write these polynomials in the canonical base for facilitate the computation of the moments of the form from the functional equation. The class is equal to 3 in both cases. And we remark that for some values of the parameters, we obtain major simplification. So these particular values deserve more attention. Here are the results for the fine Stieltjes equation. We determine again the class, and we obtain 3, has the class of this perturbed form. From the coefficient of the fine Stieltjes equation, satisfied by the perturbed form, we can obtain recurrence relations for the coefficients of a structure relation satisfied by perturbed polynomial. So the structure relation relates the polynomial Pn plus 1, and the derivatives of Pn plus 1. So the recurrence relation are given in terms of the perturbed recurrence coefficients with this initial condition determined from the polynomial C and D that appears in the Stieltjes equation. Now, our main goal is to find closed formulas for the coefficient of the structure relation. So, from the preceding recurrence relation, we compute recursively a table of the first coefficient up to a maximal order and write them in the canonical base. From that results, we determine a model to the closed formulas of Cn and Dn by applying an interpolation procedure. This is a detailed work and is the difficult step of the algorithm. And this is possible also because the degrees of Cn and Dn are bounded by S plus 1 and S, where S is the class of the perturbed form. When we determine the model, we prove we give a demonstration by induction of the model using again the same recurrence relations. Here are the results in the dilation case. So we write the polynomial, the coefficient Cn in the canonical base. The degree is equal to 4. So the class is 3, so the degree is equal to 4. And we have the coefficients here in terms of the parameter of perturbation. The degree of the coefficient D is equal to 3. And we have also the formulas for any n, any degree in terms of the parameter of perturbation. The perturbed orthogonal sequence satisfies the following second-order linear differential equation, whose coefficients are given directly from the closed formulas of Cn and Dn by these identities. So we have here some difficulty due to this sum, but the main difficulty is find the closed formulas of Cn and Dn because these equalities are direct. Furthermore, the degrees of these polynomial coefficients are bounded by expression depending on the class. So here are the results in the dilation case for r equal to 1. We have different formulas for even or odd degree, the coefficient j, k, the L coefficient for even degree, and the L coefficient for odd degree. So we obtain big formulas. So now we are going to explicit results in some particular cases. So in the dilation case for lambda equal to 1. So this is the gamma coefficient which is perturbed. So we obtain the generative function, the transfer polynomials, the closed formula for the Stieltjes function, the coefficients of the quadratic Stieltjes equation, and the C coefficient vanish, the functional equation, and the class is equal to 1. The affine Stieltjes equation, the D coefficient disappear. The coefficients of structure relation, Cn and Dn, are quite simple. So we have identified a perturbed sequence more simple than the original sequence, and this is very interesting. Indeed, the coefficients of the differential equation are quite simple. So that's all. Thank you for your attention. If you have any question or remarks, please send me an email.